Hello everybody, it's Tarun. Welcome to your fifth tutorial in the signal system and control course. Okay, in the last tutorial we talked about convolution sum and convolution integrals. Okay, and in this tutorial we'll talk about properties of linear time invariant systems. Okay, so now let's move forward and start with the properties. Okay, so linearity and time invariance property is already there because we are working in linear time invariant systems, so it means that the system will be linear and time invariant. Okay, and they are completely characterized by the impulse response. Okay, impulse response is represented by h. Okay, this function is impulse response. So you know that in discrete case the convolution sum is this, and for a continuous time the convolution integral is this. Okay, so the properties which we are going to learn are based on and will be represented in terms of impulse response only. Okay, so first property is cumulative property. Okay, cumulative property means that order do not matter of the signals. Okay, they can be convolved in any order. Okay, so in continuous time case, if I am convolving xt and h of t, okay, and ht and x of t, okay, then the formula which is h of tau x of t minus tau d tau, or x of tau h of t minus tau d tau, okay, both will yield the same result. Similarly, in case of discrete time, the summation term h of k into x of n minus k and x of k into h of n minus k will yield the same result, which is different convolution sum for h of n and x of n, and x of n and h of n. Okay, so these are the implications, okay, which are based on the cumulative property of the linear time invariant systems. Okay, these are same which I have told you, just written here, so you can read them. Now let's move forward to the next property, which is distributive property. Okay, so in continuous time case, okay, if I convolute h1 of t plus h2 of t with x of t, then I can also calculate that individually also, x of t and h1 of t plus x of t and h2 of t. Okay, similarly for discrete time case you can do that. Okay, so what does it imply? It implies that it represents parallel connection of two LTI system represented by single equivalent LTI system. Okay, so you can think of it in this system. Okay, so what is happening here, that you take x of t and then pass it with h1 of t, okay, and x of t with h2 of t, and take both convolute to differently and then they sum together. Or you can do that, you sum the h1 of t and h2 of t and then pass x of t to get the result which will be same in the first case. Okay, so these two outputs will be same. Okay, so now let's move to the associative property. So if I am convoluting xt, h1 of t and h2 of t, and if I am calculating h1 of t and h2 of t first, then the output of h1t convolution h2 of t with x of t, then it is equal to x of t convolution h1 of t, then the output of this convolution with h2 of t. Okay, so this is the associative property. This is similar for discrete case. Okay, so this is the implication of series LTI system or cascade connection of LTI systems. Okay, you can see that when I pass x of t through h1 of t, then I will get, say, w of t, okay, which is equal to x of t convolution h1 of t. So now when I pass w of t through h2 of t, then y of t will be equals to h2 of wt convolution h2 of t, okay, which is similar to x of t convolution h1 of t convolution h2 of t, okay. So these both will yield the same output, okay. So you can also use associative and cumulative properties together, okay. You can see that here. This is the expression, okay, how to represent it with the block diagrams. First I pass x of t with h1 of t, then here I will get x of t convolution h1 of t, and when I pass it through h2 of t, then y2 of t will be x of t convolution h1 of t convolution h2 of t. And but in this case, when I pass x of t through h2 of t, then here it will be x of t convolution h2 of t, and when I pass it through h1 of t, then it will be x of t convolution h2 of t convolution h1 of t, okay. So y of t will be both the same, okay, which is a result of associative and cumulative property, okay. So these are the proofs of certain properties, okay. I am not going to discuss them, they are easy to understand, so you can go through them and understand them, okay. So now let's see the relationship between LTI system properties and impulse response, okay. So first see LTI system with and without memory, okay. First you recall that memoryless systems, so output depends only on the present value of input signal. So let us consider the discrete time case. Here k is summation k is equal to minus infinity to infinity x of k and h of n minus k, okay. So I have taken the output y of n equals to k x of n, where k is a constant. It will be only possible when h of n will be equals to k times delta of n, okay, or k is equal to h of 0 delta of n. So if I put here h of n instead of h of n, k delta of n, then it will you can say that at n equals to 0 this will exist only, and at n equals to 0, so delta of n will be 1 and the resulted output will be k x of n. Similarly, for the case of continuous time LTI systems, you can check that, okay. So for identity system, okay, if I take k equals to 1, so then x of n will be equals to x of n convolution delta of n, and x of t will be equals to x of t convolution delta of t. The identity system says that when you take the value of k equals to 1 from the above case, then you get the output same as the input, okay. So the input will become the output, okay. Now let's check the invertibility of LTI systems. Okay, invertible LTI system has LTI inverse. So for the invertibility, this statement is the main statement for the invertibility property, okay, which says that the inverse system and the original system and their convolution will result into an unit impulse system, okay. Similarly for the continuous time case, okay. So now let's see with an example. You have accumulator where h of n equals to u of n, and y of n is the convolution sum, and if I put u of n minus k instead of h of n, which is the h of n's value, okay, so this will be valid from minus infinity to n, okay. So the output will become k is equal to minus infinity to n summation x of k, because this will become 0 when k is equal to k lies between n and infinity, okay. So you can note that u of n minus 1, u of n minus u of n minus 1 will be equals to h of n minus h of n minus 1 from this equation, okay, and which will be equal to delta of n. So inverse function of this will be delta of n minus delta of n minus 1. Okay, so there is a differentiator which is a differentiator, okay, for the discrete time case. You can see it in the book in the example 1.4.4. So now let's see the causality of LTE systems. Okay, in the first unit I told you that causality means that the output of the system depends on present and past values. Okay, but now what we are going to define that the impulse response will be 0 for n less than 0 in the discrete case, and h of t will be 0 for t less than 0 in the continuous case. Then if a system follows this property, then it is a causal system. Okay, now let's see the stability of LTI systems. Okay, stability in the first unit I told you that follows Bibo property, which is bounded input bounded output property. So now if I take x of n is a bounded input for all n, then let's see what happens to output. So output we have taken mod outside. So if I take the modulus inside, then the equals to will become less than equals to. Okay, and I can replace this x of n minus k with bx, and the rest will remain the same. So this the whole term I can say py, which states that your y of n, which is the output, is a bounded function or a bounded signal. Hence it is the sufficient condition for Bibo stability, and hence your system is stable. Okay, similarly you can see for the continuous time system, okay, that h of t must be absolutely integrable. Absolutely integrable means that mod of that function from minus infinity to infinity with integration should be less than infinity. It must be finite. Okay, so now let's see an example. Let's take an integrator where h of t is equal to u of t. So if I integrate minus infinity to infinity, my mod of u of tau d tau, okay, then it will, the u of t function is 0 from minus infinity to 0. So the limit will change to 0 to infinity, and the value is 1 here. Okay, so if I integrate 0 to infinity 1 d tau, it is equal to infinity. Hence it shows that the system is not stable. So this is the summary of all the properties which I have told you, that for memoryless, take h of n is equal to delta of n and h of t is equal to delta of t. Invertibility states that h of n and h of inverse of n's convolution will be equal to delta of n. Similarly for the continuous time case. And for causality, h of n and h of t both are 0 for n less than 0 and t less than 0 respectively. And for stability, summation minus infinity to infinity and integration minus infinity to infinity, h of n and h of tau d tau both are absolutely integrable. Okay, so now let's see the last topic of this lecture, okay, which is unit step response. Okay, earlier we studied impulse response, which was represented by h of t, but the unit step response is represented by s for continuous s of t and for discrete s of n. Okay, so h of the h function was related to delta function. So here you can relate it with that. If h was related to delta, okay, so unit step and it was called impulse, so the unit step will be related to the u function. Okay, so now let's see the relationships. So s of t is equals to u of t convolution h of t, and s of n equals to u of n convolution h of n, and you can do it with the help of formula also. Okay, so the properties which h of t and h of n will follow are: h of t is differentiation of s of t with respect to t, and h of n is equals to s of n minus s of n minus 1. This equation is called differential equation, and this equation is called difference equation. Okay, this is differentiation equation or differential equation, and this is difference equation. Now let's see an example. We are given impulse response h of t is 1 upon rc e to the power minus t upon rc u of t. So if we want to calculate s of t, so how you can calculate that? It is minus infinity to t h of tau d tau. Okay, you can relate it with the running integral property which we studied in the unit 1, okay, and the summation property which we studied in unit 1 of continuous and discrete time respectively. So if I calculate s of t, 1 upon rc is constant, it will come out of the integration. Okay, and we are calculating minus infinity to t, but the h of t has u of t inside it, so it will be integrated from 0 to t only, and it is e to the power minus tau upon rc d tau. So if you solve the integral, you will get this answer, which is the step response for the impulse response given here. Okay, so this was all in this tutorial. Okay, we have studied till now the convolution sum, convolution integral, and the properties of the linear time invariant systems. In the next tutorial, I will teach you the last topic of this unit, which is difference and differential equations. So thank you guys for watching. I will see you in the next tutorial.